You're listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're going to be checking in with leading industry experts and, of course, our very own Wurth Elektronik technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, as well as crystals and timing devices. So tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast. Frequency products are the heartbeat of a lot of electronic circuits. They play a very crucial role in their symphony. But if there is something that we do not want in our electronic symphony, it's unwanted noise. And in this podcast, we'll be giving some insights into the integration of an oscillator into the symphony. Beginning with the choice of oscillator, we're going to be looking at various types of unwanted noise and the measures that can be taken to optimize the design up to specific PCB layout recommendations, all to harmonize your oscillator with all your signals to ensure your success at the EMI testing lab.
So let's get started with the symphony of oscillators. Let's have a quick look at our today's agenda. So first of all, I'm going to start with a short introduction, and afterwards we will directly dive into the topic about the types of noises that could occur when using an oscillator and going for an EMC measurement. There we do have usually three kinds of noises from the oscillator itself, from the power line, and also on the output line from the oscillator to the microcontroller. We will look at all kinds of noises and what you can do during your design phase to reduce or even eliminate all kinds of noises and have no problems at the EMC measurement later on. At the end, we will also have a look at the PCB layout recommendations, because the best filtering can't do magic if the PCB layout is not very good. So let's get started with a short introduction. So first of all, what is EMI and EMC? Of course, the most of you know it. It's electromagnetic interference and electromagnetic compatibility. But what does that mean? So in general, when we now look around, we can see that there is more and more number of electronic devices all around us. Especially since Corona, the number of electronic devices even more increased. And we need to make sure that all these kind of electronic devices do not disturb each other. And that is what the EMC regulations are for. So we need to ensure that there are specific regulations in place to limit the emissions and interferences devices are getting out, so that we don't disturb other parts. And also we need to ensure that our electronic device is not interrupted by any other device. I think we all still can remember the times when we heard a mobile phone already ringing before it was actually ringing in the radio, because we heard it did. That was a typical case of interference that we don't want to see and hear anymore nowadays. But what does that mean in respect of oscillators? Oscillators are in many cases the heartbeat of a circuit. Without the clock of an oscillator, many functions won't work as they do at the moment, and they are, as said, the heart to the microcontroller, which is usually the brain of a circuit. And to protect our heart of the circuit, we need to make sure that we also have some measurements in place. Because oscillators can be affected by EMIs, so by interferences, but also on the other hand, they could generate interferences. And of course, we need to ensure that this doesn't happen. And in general, we need to take appropriate measures to prevent any interference to get out. And how this could look like, we will see in the following slides and talk about. So now let's directly start with the oscillator and the type of noises. As mentioned in the beginning, there are in general three kind of noises we see around the oscillator. On the one side, it's from the power line that comes to the oscillator. It can be from the oscillator itself, or it could be the output line that builds up some interference for the circuit. We are going to look at all three of them and in detail, and we'll start with the noise from the oscillator. In general, first of all, I want to say that presentation and all of the recommendations are mainly for crystal-based oscillators. That is what I have been looking at, and that's what my experience is with. So if you are using a MEMS oscillator, it might not be 100% applicable. So please be aware of that. When we look at the oscillator itself is seldom a problem. Usually it's the noise from the input line or from the output line that causes any kind of noise. However, the IC within the oscillator, or also the connection from the IC to the crystal blank within the oscillator, could lead to a little bit of interferences. However, there is some things we could, missing the English word, sorry for that, that we could, I will rephrase my sentence, sorry for that. So there is some things that we can change or do with the choice of specific parameters when we choose an oscillator already that have an influence on the EMI. And that is the first thing we want to look about. So what can we do with the choice of oscillator that influences the EMI? First of all, it's already the type of oscillator. Usually, most of the time, the type of oscillator will be already made by the overall application that we are looking. Like for example, an 060 we wouldn't use if we don't need it. So if you have, for example, a very stable application you're looking for, then you might use an oscillator, an 060, so an oven-controlled crystal oscillator. However, an oven-controlled crystal oscillator 060 is very good when it comes to EMI, because usually a 060 is using very high quality components and already has a very good layout, very low phase noise within the circuit, and therefore the emissions are pretty low when it comes to EMI. On the other hand, a 360 has a controlled voltage, so that's what it stands for, a voltage controlled crystal oscillator. And whenever you have the chance to change something with the change of a voltage, then it is also susceptible of interferences, and it's not so good for EMI issues. The same is for T60s. Within a temperature-controlled crystal oscillator, you do have a compensation circuit. And again, there you adjust the frequency with the temperature from outside. So it is susceptible for variations and may introduce noise to your circuit. On the other hand, a standard XL is quite a good compromise. It doesn't have the high quality components from an 060, but on the other hand, it also doesn't have any control circuit or compensation circuit. The next parameter we could influence the EMI is with the size. Usually we often say bigger is better, but in that case, we have to say smaller is better, because simply larger parts mean longer traces and larger antennas, so they make more efficient radiators. Additional, they probably bring more parasitic elements like inductance or capacitance or resistance to your circuit. Therefore, smaller is better when it comes to the size of oscillators within your circuit. The next point we look at is the output signal. Of course, this is usually given by the microcontroller you are using. But just keep in mind, if you are using a rectangle or square wave output like CMOS, of course, it's usually the most easiest one for the microcontroller to use. But on the other hand, the square wave output is done by adding a lot of harmonic frequencies to get to that square wave. And therefore, you will also have a lot of harmonics within your EMI spectrum or EMC spectrum. The next one, sine wave, is when it comes to EMC, the best one, because it's a single clear frequency that comes out of your oscillator. On the other hand, it is very sensitive, so especially to interferences from outside. So you must take very good care on a sine wave signal if you use it. A differential output, like for example LV-PECL or LVDS, is usually very good if it is designed properly on your layout. So it means both differential lines must be the same length and close to each other. Then it is pretty good for EMC considerations. Next point we can have a look at is the rise and fall time. And here we can say, take it slow. The slower, the better. It simply influences the harmonics and spectral content and edges of the output. So if we have faster rise and fall times, we will see also sharper edges and more frequency, high frequency spectral content. Therefore, if you can use a slower oscillator, go for it. And one point I want to mention here is if you have a look into the data sheet of an oscillator, there's usually a number for the rise and fall time. And I would say in most cases, don't believe that because usually oscillators are much faster than it is updated in the data sheet. So if it's of importance for you, go ahead and ask your oscillator supplier for some measurements to know the real number for the rise and fall time. Frequency, so the most defining parameter for oscillators. Again, here we can say lower is better. Just because higher frequencies make smaller antennas. So the perfect antenna length is depending on the frequency. And it's more likely to have a good radiator antenna on your PCB if you are using a higher frequency. So if you have a choice on the frequency, go for a lower one. And last but not least, the supply voltage. Of course, this is usually also given by the circuit. But again, if you have a chance to influence it, I would recommend to go for smaller supply voltages. Supply voltage or smaller supply voltages mean we also have smaller signal levels, lower signal levels, which of course can cause less noise. And additional, the positive side effect of it is usually if you use less supply voltage, you also have less current consumption. So much about the choice of specification parameters for an oscillator that we can use to influence EMC. Let's now have a look to a very special oscillator. So in literature, you will find a lot of recommendations towards a spread spectrum oscillator if you look up oscillator and EMC. But this is probably only in literature because in practice, this is a solution we see very, very seldom. Spread spectrum oscillators are basically only probably a solution if you have no space for filter components around your oscillator, or your design is already finished and you fail doing the EMC measurement, you don't want to change anything except of the oscillator, then you might change XO, a standard oscillator, with a spread spectrum oscillator. But usually this wouldn't be your first choice. But anyway, we're going to have a quick look what a spread spectrum oscillator is and how it is working. So I have here the spectrum measurement of a CFSS2 oscillator at 50 megahertz. As you can see here in the middle, that's the 50 megahertz. So it is basically perfectly how it should be. The resonance frequency has a very sharp and high amplitude. So this is how you usually want to see a crystal or an oscillator to work. However, if you now have problems with the amplitude of the 50 megahertz or with the harmonics of the 50 megahertz and use a spread spectrum oscillator, you could put on the spread spectrum modulation and it will look like this. So here you can see, for example, a 1% spread spectrum modulation. This means that a frequency of 50 megahertz plus minus 1% of the frequency is modulated. So we now don't have the amplitude at 50 megahertz, but at plus minus 1% of 50 megahertz. So it takes down a little bit of the energy of the amplitude, and therefore this causes less problems at the EMC measurement. So much about the oscillator itself. Now let's move on and have a closer look to the noises that come from the power line. So first of all, it is pretty important or very important to have a very stable and clean power line. It should have a good ground connection and it should have a low level of impedance over the broad frequency band. To provide that and to support that, there are several measures we can take, and this is what we're now going to look at. The first recommendation I want to give is the decoupling capacitor. This is usually also given in all data sheets of oscillators, and therefore it's a minimum recommendation to add a decoupling capacitor, or also called bypass capacitor, into your circuit. This kind of capacitor isolates AC from DC signals to ensure that the oscillator only sees a clear AC signal. And additional, it is an energy storage. So whenever the oscillator is clocking on the outside, it pulls current from the input, and to ensure that the energy is always present and the oscillator works without any interruptions, it can get the energy from the capacitor. So therefore, it ensures a stable supply voltage. And now, if we choose the capacitor already correctly, then it can also act as a filter and shunt some high frequency noises to ground already with the decoupling capacitor. How this choice is done with the decoupling capacitor, we are going to look now. The standard recommendation for most of the data sheets of oscillators is either 10 nanofarad or 100 nanofarad. However, not every 10 nanofarad capacitor is the same. So here the devil is really in the detail. If we want to use a decoupling capacitor at the choice, we need to have a look at the DC bias diagram of the capacitor. So let's have a look at the DC bias diagram. This one, I choose three 10 nanofarad capacitors and 3 100 nanofarad capacitors, having a little different sizes and different rated voltages. In general, the DC bias says how much capacitance is my capacitor losing with increasing voltage. So yeah, with an increasing voltage, a capacitor simply can't deliver all of its capacitance anymore. And this is important when our capacitor should act as a decoupling capacitor. As said, I have chosen 3 different kind of capacitors, each value. And now let's simply assume we do have a 3.3 volt oscillator. As we can now see here, 2 capacitors already lost a lot of their capacitance. So this one, the orange one, already lost 30% of the capacitance, and the brown one already 40% of their capacitance. So if we would have chosen one of these 2 as a decoupling capacitor, it couldn't do his work. And we would be a little bit lost why it's not working. If we now even look at the 5 volt oscillator, then we can see there are another 2 capacitors that are already decreasing in their capacitance. This is only 4% and 6%, so it still could be used. However, it's not ideal anymore. And that's why I want you to remember to have a check on the DC bias when you're designing in a decoupling capacitor. If we now also want to use the decoupling capacitor as a filter element, we will have to have a look onto the impedance curves. So here we can see the same capacitors that we saw before. And again, you can see the curves are looking different for all kind of the capacitors. If we now assume we do have a 20 megahertz oscillator, you can see it is already above the self-resonant frequency of the first capacitor. During the phase before the self-resonant frequency, the capacitor acts as a capacitor, and this is where we want to be. Afterwards, in that area, it is inductive, and this is not what we want to, because then it can't filter anymore. So to have it as a filter, it must be on the left side of the self-resonant frequency, but also it should be low in resistance or impedance at the oscillator frequency. If we now assume we do have a 50 megahertz oscillator, we can see there are another 2 capacitors that wouldn't filter anything. If we now have a look at the values, we can see all the 100 nanofarad capacitors would fail to act as a filter. So again, if you want your decoupling capacitor also to filter, please remember to have a look at the impedance curve, for example, via the Red Expert, to see if it is in the correct area to act as a filter. Of course, the decoupling capacitor can't filter a lot, so therefore it is recommended to add some more filtering to the power line. So we are looking here for low pass filters, so it needs to pass the low frequencies and block all the high frequencies, so they don't get to the oscillator, and especially that they don't get to the MC measurement. Theoretically, all filter components we are adding at 20 dB of attenuation per decade. Of course, this is only a theoretically value. However, it's a good starting point if you, for example, have your EMC measurements taken and see how much attenuation you need. Then it is for you a good idea. Good to get an idea of how much filter components you need to add. Ideally, for our oscillators, you get your filter to filter up to 10 harmonics. So if we stay with our example of a 50 megahertz oscillator, your filter should filter up to 500 megahertz. There are various filter topologies, but we only want to have a closer look to the most common one, which is the CL filter and the P filter. So let's start with the CL filter. Some of you may mention, okay, this is already a P filter because we do have two capacitors and the inductance here. That's true. However, we will see the decoupling capacitor C1 in this case as an extra capacitor and only have a look at the CL filter. So this one is a minimum recommendation for a layout. So if you're doing a layout, it's really helpful if you already consider to add that kind of filter. So if you need it, it will be already there. As we do have two filter components, it theoretically adds 40 dB attenuation per decade. And here is a simple formula. However, it's only theoretically simple. In general, the resonance frequency of your filter should be at 1/10 of the oscillator frequency. So if we now again look at our 50 megahertz example, the resonance frequency of your filter should be at around 5 megahertz. And this is also a value that we need to consider when I say the formula is only theoretically pretty straightforward, because the inductance L is changing with the frequency. So below the value of 5 megahertz, it is usually a choke that you are using, and above 5 megahertz, it's a ferrite and not a choke anymore. So that simply makes it a little bit difficult when calculating the inductance with that formula. Yeah, so also as said, with above 5 megahertz, use a ferrite because a ferrite only starts filtering at 1 to 2 megahertz. So if you're using, for example, a 32.768 kilohertz oscillator, a ferrite wouldn't do anything. It couldn't filter anything because, as said, it only starts with 1 or 2 megahertz. So keep that please in mind when you are creating your CL filter. Now have a look at a P filter in addition to our decoupling capacitor. This one adds, in theory, around 60 dB per decade. Of course, it will be less in praxis. However, as said, as a starting point for you to know, it's good. One question that often comes here is if C2 and C3 should be the same value. And this is basically up to you. If, for example, the component size of C2 and C3 is getting pretty big because of the filter frequency, then you might use two different values because you don't want to have two very big components. So that might be a case where you choose them differently in value. So much to the filtering on the supply input of the oscillator. Now we're going to have a look at the output line. Basically, this one is the most critical one with the biggest impact on the oscillator. So it has the biggest influence. And here we definitely need to make sure that the output line won't get an antenna for our frequencies. So here we just need to be sure, especially that it is very short and the oscillator is located close to the microcontroller. Additional, we need to ensure that the output waveform that comes out of the oscillator is keeping its properties. So what usually or what often comes out of an oscillator has undesired signals like overshooting, undershooting, ringing, and echo. And these are elements that we don't want to have on our output line. So here we also use some measures to prevent that. The first measure to do so is a serial resistance that is between the oscillator and microcontroller. This, I would say, is also a high recommendation to be added as a mounting option, or to be at least equipped with a 0 ohm resistor to ensure it is there if you need it. So this resistance already eliminates the undesired waveform distortions. So as I mentioned before, the ringing, the undershooting, the overshooting. To get to the ideal value of that resistor, it is just by testing. So yeah, basically just at your oscillator, look at the output waveform, and yeah, once you have the desired waveform output, then you have the correct value for your resistor. Another option that we would recommend as a mounting option is the RC filter. So the RC filter is usually a pretty, let me see, cheap filter, but it is in the most cases sufficient enough to filter. So yeah, we do have around 20 dB attenuation. So it's two elements of a filter, but the resistor is not that high in quality when it comes to filter like the above mentioned or before mentioned. So there we only have like around 20 dB of attenuation. The cutoff frequency for that kind of filter should be higher than the oscillator frequency. So we ensure that we don't filter out our oscillator frequency on its way to the microcontroller. Usually we say as a rule of thumb, around 5 times higher than the oscillator frequency. Here we see the formula, and in that case, it really is pretty straightforward. So nothing you have to consider in here. If the 20 dB attenuation doesn't be enough, you still have the option to use also an LC filter at the output line. However, this is not that often the case. Another resistor I want to mention is the termination, or also called impedance matching resistor. This is between the oscillator and ground. Yeah, impedance matching is often a topic, and it also sounds very easy theoretically, that the impedance between input-output just needs to match. However, the difficulties here are that the impedance is very seldom known. Like for example, with the oscillator output, you may ask your oscillator provider about the impedance, and I would say in most cases they can't tell you the output impedance of the oscillator, and therefore it makes it difficult to make impedance matching. The good thing is that this one is mainly important when you're having very long traces. So if it's not possible to have a short trace between oscillator and microcontroller, then we should, or you should add this as a mounting option. Another case where you might need that termination oscillator is when your oscillator is powering more than one microcontroller or more than one user. Then it might be also necessary to have impedance matching and that kind of resistor. And finally, let's have a quick look at a very special case. the special case that you are using the RC filter in addition to a termination resistor. And here you have to take care that the both resistors build a voltage divider. So you must ensure that RS is very, very much smaller than RT, like 100 to 1,000 times smaller, to ensure it doesn't do not wait the voltage loss that is occurring, and that your signal is still good enough for the microcontroller to work. When we talk about EMC and EMI, there is also shielding often come on the table, and I don't want to miss out on that when it comes to oscillators. So let's have a first look on the effect of the oscillator housing when we talk about shielding, because some may think that an oscillator already comes in a metallic housing or enclosure, so it should already shield off some of the radiations. But I need to tell you, no, it's not the case. So if you have an oscillator, for example, with a plastic enclosure, it doesn't have any effect on shielding. If you're using an oscillator with a metal lid that is internally not connected to the ground, it will only have a very minor effect on shielding. And if you use oscillator with a metal lid that is connected internally to ground, you still only have a very small effect. So yeah, please just keep that in mind. The housing of the oscillator itself doesn't have any shielding effect. Of course, you may enclose the oscillator, probably together with the microcontroller, in another metallic enclosure or shielding can. However, that is more or less untypically. What is sometimes used in practice is an additional enclosure around an O60 or T60. So if you're looking for a very, very stable frequency, then you might want to add another closure, but that is not for EMC issues, but more to prevent environmental influences to get to the oscillator, like wind or temperature changes. However, as said, they barely have any shielding measures. Now let's come to the last point of our presentation for today. These are the PCB layout recommendations. First of all, let's start with some general notes that should apply to all kinds of your circuit. And first and foremost, keep the traces as short as possible. This is really the most important recommendation we can give you, and it should be taken care of whenever possible. Additional, avoid 90-degree bends and round right angles, because they could also have an impact on the impedance. Furthermore, do not cross any other signal lines or route signal lines under or close by the oscillator. Again, they could disturb the signal, the oscillator, and could add impedances to your system. Also, try to not get any loops, like current loops, in your system, or keep them as short as possible. And finally, I mentioned that before, keep differential outputs, output traces the same length and very close to each other to avoid problems here. And finally, let's have a quick look on oscillator-specific PCB layout recommendations. First of all, starting with the connection of the oscillator as close as possible. I'm not getting tired to say that. So as close as possible to the Xtal in pin of the microcontroller, and in that case, leave the Xtal out pin open from the microcontroller. Additional, apply best grounding practices to your oscillator. So maybe you can use a wire fence or cut out a ground plane under the oscillator. Then we already discussed that the decoupling capacitor or filter, keep it as close as possible to the oscillator, and ideally have at least an option for your mounting to have a decoupling condensate capacitor and a filter capacitors or elements. This is something I didn't mention before, but is also important when it comes to the layout, is adding a pull-up resistor. So oscillators usually have on their fourth pin, for example, an enable or disable function or a standby option. If you are not using these options, please do not leave that pin open because you want to ensure that you have clear switching states, and you can only have that if you use a pull-up resistor on that pin. So as said, if you're not using that function, please use a pull-up resistor. And last but not least, between the oscillator and the microcontroller, have at least a mounting option for a serial resistor and ideally for an RC filter. And if you are having long traces, you may also want to consider to have a termination resistor added.
Join us online and view our vast array of electronic and electromechanical components. You can also register for all upcoming webinars at www.we-online.com/webinars. While you're there, you can browse Wurth Elektronik's crystals and oscillators in order to be successful at the EMI testing lab. You could also test drive the online tool Red Expert completely free of charge. Using this tool, you can download datasheets, make comparisons, and easily order free samples directly from the website. To view the materials discussed today and to replay the video, please check out the Wurth Elektronik Group YouTube page. You're listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast.